Uh, the course has several concepts that we discuss. So getting toward your exams, but also to be able to understand uh, the essential skills, which we haven't made a lot of practice on in terms of using tools, but to be able to make use of the skills in, say, your thesis or exams, those concepts are important. I don't need to repeat the concept, but I can point out things I think are useful for you to think about and take note especially of differences when you're looking through the lectures. For instance, if you say the main components of statistics as a whole, but also in this course, we started off by saying that the goal was to organize data, to analyze data and interpret data. And those in turn can be broken down to specific activities that we've discussed along. But if you were to think of it as a two main branches, one is that you do descriptive and the other one is that you do inferences. And one thing to keep in mind is that even though you describe things with methods, it doesn't mean that you don't get insight from those descriptions. For example, if you summarize data with a graph, it's providing you already with information that might help you to make some conclusions. So in some sense, you are kind of inferring, but not in the very sense of, let's say you have a sample and then you want to learn about the population through the sample. That's the second part here, which we're saying inferential statistics is much more narrow. The first part is just, okay, I have this data. What does the data say? You explore the data, you maybe make graphs from the data, maybe you look at the mean. That's what we mean in the first one here. So the two essential parts are these parts, like if you were going to think of it as two groups of activities that statistics cover. And then in turn, each one has specific concept and techniques that you can use. If you were looking at students' course in an exam, if you had 150 students, it's not very obvious for you to answer the question is of how are the students doing. The easy way for you to think of that is more that you can look at the average of the 150 students. And when you have the average of the students, it doesn't say anything about the student population as a whole. That's inferential statistics. It says something just about the class that you have. That's the summaries. So it doesn't help you to do an inference. The mean doesn't help you to do an inference. But if you wanted to then say something about how the student perform in that course as a whole, when you only have the class, that's when you talk about inferential statistics, because you want to infer how the students do as a whole. So it's important to keep that difference in mind. I don't need to repeat this, but we also said we have different types of data, and we said we try to understand what these different types are and what you can do with that, and you can calculate the mean and so on. So in the exams, it's good to be able to distinguish what type of data is what. So if you're given an example or some data and asked to define or asked to give examples, you should keep this in mind at the minimum. Then beside this, we also said two ways of looking at data was to think of it as whether you are looking at, or at least on the level of summarizing, was to think of it as a spread or as a single summary. And a single summary is, I said, was very good if you have numbers that sort of, well, as an example, you have numbers that are similar. But if they are different and their differences are varying a lot, then you are interested to also use those concepts to describe your data. You can, using that information, you can apply different tools or methods and techniques. And it's important to know the difference between these two, which is the central location and the boundaries, as I have mentioned all along. For the central location, then we're talking about things like mean and different types of mean, median, mode, and so on. But for the spread, then we're using words such as range, variance, standard deviation, which we have used all along the course. You see, it's very easy to think of it from the names, because for the range, if you say something is ranging, you want to know the boundaries in terms of the minimum and the maximum. So the range would be the difference between those two, and the variance would then be the square of the differences divided by the degrees of freedom, which is n minus 1, and then you sum up those squares. And for the standard deviation, you just take the square root of the variance, and you get the standard deviation. So the concept remains the same, whether we are talking about a group, whether we're talking about two groups, whether we're talking about three groups, you still calculate them the same. Whether we are talking about using the standard deviation in another statistics, it's still the same standard deviation. It's not the different one. So those are very basic concepts that you should be able to know going forward to the exams. Then we left those two. Either we are looking at the central location or the boundaries or the variation of the data, and we started talking about how you can do a statistical technique, sort of rely on the theory of statistics to be able to do some sort of inference. And then we went into talking about sample t-test, different ways or different methods, you can say, using mathematical formulas where you could do different tests. We introduced the idea of a hypothesis as a way of setting up a test. And then we discuss, and one of the main core examples we've been using is the student t-test, which you would also hear it as a t-test or a student t-test, which can be computed depending on several different conditions, as we've seen. Why do you use it? Because you might have you want to make an inference, and you want to be able to use your sample and be able to say something about your population. So we use those basic statistics in computing this, and the basic statistics are, in this case, is nothing but the mean. We use the mean, two types of mean. One is for the sample and one for the population. We also introduce concepts such as sample, such as population, such as sampling, different types of sampling, and so on. The same mean that we've seen here, that we showed here, which is the mean where you add and divide by the total number, is the same mean that we're using here now. The same mean here, the only difference is that this one is for a sample and one is for a population. And the same standard deviation that we showed here, which is the square root of the variance, is the same that we're using here now. And n here is nothing but the number of how many instances we have. This formula, you should know that from primary school. This is the square root, right? So, and I also use the term error in approximation to refer to this, because this measures how far away your statistics might be from, or your sample statistics might vary with respect to your population. And we could use this and do tests with these values, and we could, in different ways. We could also use this again. We say we can calculate these basic statistics. We can use it to do a t-test, and we can use this test into a confidence interval analysis as well. So it's sort of a composite. We compose these levels of statistics using this one, and then we compose the confidence interval using this approximation as well. So if you have a problem where you need to do this, I don't know, I think there might be, but if you did, maybe you would need to know this formula. On the other hand, it might be very useful if you are doing your thesis and you want to prove something or show that your sample, or generalize what you find in your sample to the population. We started talking about not just the test for a single population. We also talked about the test when you have PACE, which we did yesterday. And here, yesterday we didn't talk about an example, so I thought maybe showing an example could be useful. When we say we are dealing with PACE, and another name for it is also matching. When we say matching, what we are simply talking about is a situation where you have two groups, at least, where for every measurement you have in one group, there is a corresponding measurement in the other group. I mentioned examples yesterday, such as if you are doing a study on twins, for example, then you have for the same person in group one, you have the same person, the corresponding person or the twin in group two. If you were doing a study on the same class, let's take the example of a class, in two different subjects, you would expect that the students are reading two subjects. So the same student in the first subject would still be the same student in the second subject. So this is a matching because for every measurement you have in the first group, there is also a measurement in the second group. And therefore it is PACE. So in that case, I then use this fake example. Let's suppose that you have a pre-test course. Let's say you were doing some let's say, pedagogical methods, for instance, and you have scores of students before the method and scores of students after the method. So it's the same students, you just have two groups. So they are matching in terms of that. There is always a score for the same student in the first, and there's a score for the same student after you've implemented your method. So that's a match sample, or that's a paired sample, or those are pair of you have a match sample or two groups of sample where you have these corresponding matches. So to calculate the t-test in that case, you would take the mean of the differences. So you calculate the differences between the corresponding pairs and take the mean. And the differences between the corresponding pairs simply mean that for the same student in the pre-test score in this example, you take the difference between their score in the pre-test and the post-test. If it was twins, you take the difference between one twin in one group and the other. If it was medication, you take the difference between the same person who had a certain treatment in the first and the second. And when you calculate those differences, in this example, I also mean to show that you might have a difficulty if the mean do not vary. In this example, which is not that it has to be like this in all cases. Maybe it's very rare that you have this situation, but it's a situation which shows that your your test might fail if they are all having the same differences. Basically, there's zero variation in the differences. In that case, the mean difference would still be the same because once you take those differences, you then take their mean. If this was a 4, the mean would then be 2 plus 2 plus 4 divided by 3. Because they are all the same, the mean would be 2, which is just 2 plus 2 plus 2 divided by 3. Sorry, I said divided by 3 is divided by 2, is n minus 1. So the mean will be 2. The standard deviation will be 0. And you can go back here if you are doing your revision to check that the standard deviation will be 0 by using this formula. If the standard deviation is 0, we learned also very long ago, I guess, in high school that, or maybe before high school, that if you divide a number by 0, it's infinite. You don't get a number. So in that case, this test might, oh, no, it's not in this example actually, because where am I? I was here, yes. In that case, you would have a value which is undefined because of the division by 0. So in the case where the variance is 0 between the pairs, or the variance is constant, sorry, between the pairs, you would have this situation. But as I said, this is a rare occurrence that this would happen. So this will not always be the case. But this was to let you know that the test can fail in that instance, and also to show you how to calculate the t-test when you have a matching sample. Something called independent sample t-test as well, which we're supposed to know from the course syllabus. So you want to compare instead of matching, and that's the one we have mostly talked about. Instead of if these pairs do not match, as we said, the case of the same group of students before and after, or the case of twins, or whatever pairs you might have, if they do have correspondence, then you have a matching or a paired sample. If they don't, then you have an independent sample because the two groups are different. Then you call it group 1 and group 2. Then you don't expect for the same particular measure in one group to be a corresponding measure in the other group because they are completely independent. So in that case, you calculate their means separately. You don't do it like here where you take the differences and then calculate the mean. You calculate each mean separate and take the difference between those means. And when it comes to the standard deviation, you use their separate standard deviations and you divide by the number of samples in each group or in each sample. Sorry, the variance is not the standard deviation. You recall that from here. This is the variance. It's the same variance we're using there. The square of the standard deviation is always the variance. So this is the variance divided by n1. And here we're using the standard deviation, not the variance. So the variance divided by n1 plus the variance divided by n2, the variance of the first sample, and then the square root of that. So the question, does anybody has a question here before I ask and answer it myself? If you were following, you probably would have a question going from this slide to that one. Nobody has a question? The reason I thought you would ask a question is because the formulas might look like they are not the same. Here we took the standard deviation divided by the square root of n, and here we were taking the variance. Is it still the same t-test? Yes, it is, because if we take the square root of the variance, we get the standard deviation, and then you have the square root of n in the bottom, which is exactly what we had here, right? Look back again to this formula. The standard deviation is the variance is given by this, and the standard deviation is the square root of the variance, right? So if you take the square root of the variance, you have the standard deviation. So here you have the standard deviation without anything. It's not the variance, it's just S. But here you have the variance, whose square root is the standard deviation. So it's still the same formula. It's just that this one, since we are dealing with the two different groups, we calculate their sum first of their variances divided by n, and then we take the square root. So it's still the same formula. Are you with me? Rashida too?
Yes, sir.
Confused? Confusing?
No, sir, I wish you ask where that and under there it signifies what?
The number of your sample, you have two groups, two samples, which are independent. So suppose one sample is a subject. Let's say it's educational statistics. The other subject is research methodology. Suppose, or say one group is from 5 students, another group is upper 6 students. Those are 2 groups, right? Which are independent of each other in any way. So then how many students are there in Form 5 is N1. How many, if Form 5 is group 1, how many students are there in upper 6 is N2 if upper 6 is group 2. And then you know the standard, you calculate the standard deviation of Form 5, the standard deviation of upper 6. And then you put them into this formula. These are the means of the 2 classes. That's what I mean by independent samples, 2 of them in this case. So you can use the t-test to compare the differences between those 2 groups to see how close they are to each other. If you wanted to test a hypothesis on these 2 groups that are independent. And this is just an example of using just the formula. And under what conditions should you do this? In other words, under what conditions should you do the t-test? When is your exams coming up? Do you know when your exams are coming up?
Yes, sir, on the 8th.
So,
On the on the 8th of March.
So you have a very short time to master this, and you're still, maybe you're reading other courses, I suppose. It's not good to wait until the last minute.
So we are reading this one. It's just that everything we see things here new.
Even though we call it a revision.
Okay.
Anyway, so you should look at the conditions that under which this should happen, because we've talked about it several times in terms of what assumptions. You don't just use the formulas, but you have to check the conditions. One thing we have mentioned without really saying is the degrees of freedom, which can be confusing. The number of values that are free to vary after a sample statistics have been calculated without changing the statistic. So when you take the one sample t-test, which is what we have seen here, this one here, when you take this one sample t-test, after you've calculated this sample, what is the degrees of freedom? What is the number of variables that can change? The degrees of freedom there is n minus 1. N minus 1 because we are calculating the, where was that here? So we are calculating the difference between the mean values of the n. First of all, here is your sample size, right? So we're calculating the difference between the mean of the sample and the population. And we say the degrees of freedom is n minus 1, which means that in this sample, if you were to use the same formula, the n minus 1 refers to all of the instances you have in your sample. Any of them can be anything. Those are the values that can change in your sample, because if the value of n changes, then you would have a different calculation. For this formula would give you a different calculation. So any of the n minus 1 samples can be any value. Basically, starting from the last value of n, because if you change the n value, then you change the total number of samples, and then the formula would give you something different. The degrees of freedom, in other words, is how much should my data, or what are the varying, what is varying in my data. Let's say you have, in this example, did we have an example here? The n here is 3 numbers, right? So any of these can be anything, as long as you don't go above or below this value of n. This can be anything. But if you go above, then you have n becomes n plus 1, n plus 2, and so on. And then you have a different calculation. For the independent sample t-test, you have 2 of these. So that's why you have n plus n minus 2, because you have 2 samples. For ANOVA, which we would see another example, we are dealing with differences between groups. And therefore, if you change the number of groups, your result will change. If you're talking about the within groups, then if you change the difference between the numbers within and outside of the group, then within and between, sorry, then your calculations would change as well. And for chi-square, we can think in terms of columns and rows. How many columns and how many rows do we have? And if you change any of those numbers, you would have it. We'll see these examples in a bit. So the degrees of freedom is usually talking about the total number of variation or things that can vary in your group or in your sample. As long as you maintain the same number, you would have the same, you can use the same formula and get the same result. We did not look at an example on ANOVA, but we talked about it as a statistical technique that allows you to compare when you have more than 2 groups. When you have 2 groups, we're talking about the t-test. When you have more than 2 groups, then we're talking about using a method called ANOVA. And the simple way to think about it is that you are comparing how the mean values of these groups can vary if your statistic is the mean between the groups and within the group, and you take the ratio of that. So how do you then calculate this variation between the groups? How do you calculate the variations within the group? Let's look at an example that suppose you have not just 2 subjects, you have 3. And in the first, you have some measures that you've done. In the second, you have some measures that you've done. And for some reason, you want to study 3 groups. What you would have to do is you will have to calculate the sum of squares between, and you have calculated the sum of squares within the groups. And then you divide each by the respective degrees of freedom. I would show you an example how this is done. So if you have group 1 with 10, 12, and 14 as your measure of whatever, and the group this is just a generic abstract example. And you have group 2 and group 3 as well. So what you can see here is that if you calculate the average of group 1, it will be 12. The average of group 2 will be 16, and group 3 will be 20. Now, if you calculate the average of the 3 groups, the group average, it will give you 16. So first we calculate the average of each group, and then we calculate the average or the mean of the 3 groups. So to calculate the variation between groups, you will have to then take the difference between the average of or the mean of each group and the group mean. So the group mean is 16. Group A has a mean of 12. So the difference between 16 and 12, the second group has a mean of 16. And so therefore the difference between 16 and 16, the third group has a mean of 20. And then the difference between 20 and 16. So you square each of these differences, and then you multiply by 3 because we have 3 groups. And if you do that, you get 96 in this example. So the variance between the groups, which is what we are calculating here, will be 96. So, and then you go ahead and you calculate the within And for the within, you will then take the difference between every member of the group and the average of the group. So in group 1, we have 10, 12, and 14 as the scores. 10, 12, 14. In group 1, the mean was 12. So you calculate the difference between x1 in group 1 minus the mean. Ij here means group 1, element 1, group 1, element 2, group 1, element 3. So x11 would be 10, which is the first member of group 1. The mean of group 1 is 12. The second member of group 1 is 12. The mean is 12. The third member of group 1 is 14. The mean is 12. So you calculate these differences and square them. And then you add that to the same thing for group 2. In group 2, the mean was 16. The members are 14, 16, and 18. So 14, 16, and 18. So you do the same. And in group 3, you do the same. And then you add all of these, and it gives you 24. So you then now use the 24 and 16, and you divide each one of these by the degrees of freedom. So you weight those. This is some sort of a weighted mean that we discussed earlier. So 96 here was the between, and the degrees of freedom, since we have 3 groups, was 3 minus 2, and then we have this. And for this one, the degrees of freedom within was, since we have 3 elements in each group, you will have 3 minus 2 plus 3 minus 2 plus 3 minus 2. That gives you a 6. So you weight each of those calculations by the respective degrees of freedom. And so you have 96 divided by 2 and 24 divided by 6. And then you take the ratio and you get a 12 here. So in this particular example, the ANOVA will give you a score of 12. I don't think they will give you this kind of calculations, but just an example for you to know if you have to do an ANOVA test, say, in your thesis. Having said that, I am not the one who is responsible for the exams, as you know, is coming from the University of Bamenda, and therefore, please don't just assume that or get a question and say the teacher said they will not give us this question. They may give you. I don't know if Madam Rama would like to say anything here.
Okay. First of all, I'd like to appreciate the way you have explained this ANOVA, because you have really simplified it. For their information, we cannot discard the idea of the exam excluding ANOVA. They should just take everything into consideration. So anything can come, because ANOVA is part of the program. It might come, it might not come. But then the example you have given and the way you have done it is very clear, because even what we did, we just mastered the formula and mastered all the steps. We didn't even really, we could not really explain it this way. So it's very clear. Thank you.
All right, so thank you very much. And if there's no question, we move on. So please don't take my word that I said it will not come. So I take back that. Then we talked about chi-square as well, which is a test to test the independence of categorical values. Because ANOVA, we said it was continuous values, and for the chi-square, we say we were measuring the differences this time between our observed and expected. And I showed an example yesterday of choosing between colors, which I thought was simple and straightforward. If you have people choose between 3 different colors or 4 different colors, and your expected value is just the only way, if you do not have any other evidence, is that, well, each color is equally likely, or you expect that they will choose equally from the same, or you have a reason to think that one color is more favored than the other by a certain percentage, right? Then you have a different expectation. But if you want to just do a simple example as we're doing in this case, and you say, okay, we don't have a preference. They can choose any color. Therefore, your chances would just be the total number of colors divided would just be the one color would have a chance of 1 divided by the total number of colors. And if we have 4 colors in the example we were discussing yesterday, it was 1 divided by 4, and that gave us 25%. I'm emphasizing on this expectation. How do you calculate the expected value of? In mathematics, the expected value is more involved than just a simple probability expectation. Suppose you thought that the color red was more favored, then maybe you have a 50% chance that people would prefer the color red, and therefore it cannot have the 25%, which means that the remaining 50% would be distributed to the other 3 colors. So somehow you have to have some expected value. And if you also have the conditions that we discussed yesterday to think that the chi-square is the statistics you need to use, then you need to subtract your observed values from the expected values, or the expected value from the observed value. The observed is exactly what your data is saying. That's your measurements. So then when you have data, the observed is not something you have to worry about, because you just calculate how many people choose a certain color. It can be colors. It doesn't have to be colors. It can be anything, but the observed is there. What I'm emphasizing is, how do you get the expected? The expected can be based on assumptions or some other evidence that you have. The expected, if you are an experienced teacher, you might have an expectation on students, and therefore from that experience you can know what the expected values might be. If you were going to say you were going to save a meal, or you wanted to organize a party, maybe you live in a place where most people are vegetarian, so your expected value between vegetarian and non-vegetarian, you would say that, well, most people would be non-vegetarian, so you put a higher expected value for non-vegetarian, and you say maybe 75%, and then maybe 25% would be non-vegetarian. And then when you then send an invitation and ask people to tell you what their choice of preference would be for food or for their meal, you can then get a distribution that would be observed, where maybe it came back that, well, 80% of the respondents choose non-vegetarian dish, 20% or 80% choose a vegetarian dish, and 20% choose a non-vegetarian dish. Then your expected value was 75%, or was it 70%? I said 70%, and what the observed value was 80%, because that is based on your statistics, on your data that you obtained from your invitations. And then you can use this to calculate the chi-square, to calculate how close your estimate was to the expected value. So that's like just one way you can think about it. So you can do this then for each of the categories, and you have for the first category, which would be the vegetarian, you take their measurements, subtract from the expected value, and for the second category, which is the non-vegetarian, you do the same. But this example is not talking about colors or males. This example is talking about sports, where you want to have the variation between people who like, say, different kinds of sports. Maybe some people like football, and others maybe like handball. And then you have observations where you collected data, and it turned out that 40 males like sport A and 30 females like sport B. Sport A, sorry. So in this case, you're calculating the difference between the males and females in terms of the sport they like. And then your groups are the males and the females, not the sport. And then you can get use ANOVA to do that. Use chi-square to calculate that. So this one should be straightforward. Another measure we used was the correlations, which we used, I think, in the fourth or so lecture, and we said the correlation
I
was...
have a comment to make, please.
Yes.
Let's look at chi-square again. The formula for chi-square, we have summation O minus E, all of that squared, all of that squared, all over E. We are talking about observed frequency and expected frequency.
Yes.
Yeah, I want to highlight something to them, that the example you've given is a typical example of a case where the observed frequency was that the frequencies were unique. They were not they were not gathered from a much larger sample, like what they would do when they will go for their data collection. Because after that data collection, their sample will not reflect this. They might have a sample, let's take, for example, somebody is having a sample of 30. You collected data from the 30, from that sample, from the respondent. And because chi-square happened to be a method where we are working with categorical data, where people might say you might have asked your respondent to give to answer in terms of yes or no, true or false, and so on. Now, after collecting that data, what you bring back from the field, they are the observed frequencies. Then the expected frequency can be calculated by using the formula. You will tabulate it and then use the formula root total times column total all over the general total. That's the formula you will use to obtain corresponding expected frequencies. And each time for each objective, all of the yes responses will have the same expected frequency, and all of the no responses will have the same expected frequencies. I'm trying to make the comment because they will not come back from the field and have unique observed frequencies or unique something like that. They will have to deal with a larger number, and so they need to calculate the respective expected frequencies. Maybe in class I can throw more light on it.
I'm happy with that comment, because that's as you rightly say in the last comment, that you can show them in class, which is good. And I also think those expected frequencies are sort of in line with this, because you would be calculating the expected frequency where you would be under the assumption of how likely are the yes answers and how likely are the no answers, and that you could be informed by the total number of samples that you obtained in order to get that expected frequency. And I think one reason why this is the case is because you do not know how many respondents you would have. So that expected frequency would vary depending on how many responses. And I guess the reason why you are using the number of rows of how many responses you actually had.
Yeah.
For instance, when we gave the simple example of colors, if you ask people about different colors, 3 to 4 different colors, and it turns out that nobody, the number of people who responded for a certain color was 0 in that case. So that would affect the way you do the calculations, because there were no responses for that color. And therefore, the expected frequency is not necessarily always determined before you administer the test.
Okay.
So you're right in that.
Thank you.
So one other formula that we had talked about was how to measure correlations. Correlations is a very strong statistical technique when you want to look at how explore, but also do inferences. One of the things I do in my work is also that if you give me data and I need to do some study on it or analyze it, regardless of what data it is, and it has different variables, especially because I work with machine learning. Machine learning models depend a lot on correlations. So you want to know how one variable varies with the other. And the way that you mathematically express that, not that I sit and think about how this is calculated, more is that, okay, I get a software that calculate the correlations, and the most important thing is that I can interpret what the results mean. So the correlations measure how each variation is for one variable and the other, and compare those two variables. We would see that what is Ndi doing now on his phone? Did somebody say something? Grace, please, if you possibly have some questions that can help, it will be very good. I mean, sample exam questions. That was a question from Grace. Yes, we'll look at the 1 or 2 exams questions toward the end, Grace. I think is it the feeling that you have that is not very helpful to be talking about this? I can't just specifically focus on a question because they can ask you any question. Do they have access to sample questions? I'm trying to delete this thing here that Ndi is making. Let's see. Do they have sample questions? Or do you have sample questions? Let me not be asking to one person. Do you have sample questions? I'm asking to the students. Do you have access to pass exams? Nobody's saying something? Rashida too, do you have access to pass exams?
No, sir.
I guess why not? You should have access to pass exams, I suppose. I don't know how the program is organized. You
I
should
will check on it.
ask your program manager to give you. I don't have myself access to them that I can share it with you. Or what do you say, Madam Rama?
I think we talk about that. I've not. I thought I gave them one sample. We talked about one. We discussed 1 year in class. We gave them the sample, but I've not really given them multiple samples.
Okay.
Mm.
I don't know what the policy of the program is. That's why I don't want to answer that question.
I guess one thing I've not also been thinking in that light is because they are not also like after me with those sample questions. They should be the ones to rush for it.
Yeah, exactly. If you're not asking it, then that's why I don't know what the policy is.
No, the policy they are not restricted to have access to past questions, but they just need to be more ambitious or anxious to have those questions, and then you'll get them. I think I have some.
Yeah, Grace, working with questions is more helpful. Yeah, but I also hate when students study just to pass on exams. I think knowledge is first. Exams is an evidence, not the target. You can just study only the exams and then write and pass. It's good, but how much did you really learn? We will look at some questions that are from the past exams toward the end. But still, I think it's important to have these concepts for the course, but also for your own knowledge as you leave the program.
Prof, meanwhile, you can also share the questions, some of the questions that I shared with you.
Okay.
Yeah.
I could publish some when I publish this lecture.
Yeah.
All right. So then you we're talking about correlations. Grace, is something that you cannot talk. You're writing. So for the correlations, I said you're looking at how two variables vary, and it's very important when you look at your data, if you have two variables, to really, really look whether there's a correlation. Correlations tells you a lot of things. One simple thing that correlations tell you is the amount of information that you have. Suppose I have two variables that vary exactly the same. Their statistics tend to be exactly the same. In terms of using large data sets, if I had data set with so many variables, for example, from say x1, x2, x3, x4 to x10, I can use correlations to reduce some of those. If I see that X1 and X7 are varying exactly the same, I don't need to consider both in my analysis. It's enough to consider just one because it's the same information. So correlations can be calculated by this formula, which you take the mean, the difference between every value in one variable and its mean, and then you multiply that by, you sum them up. So X1 is, say, mathematics, and you look at the scores of students in mathematics subtracted from the mean. And the second one is, say, history, and you look at the scores of the students in history subtracted from the mean. You can see how the students' scores vary in mathematics and in history. And then you multiply that and sum all of that, and then you take the same thing in the denominator individually and take the square root. So here again, if I ask the question, you take the mean, square it, and then you take the square root. Okay, it's nothing that we've seen before since it's just the differences with the mean. So this is not, it doesn't resemble any statistics that we've seen before in terms of standard deviations and so on. So this is just the difference between every measure in X and the mean of X squared, the difference between every measurement Y and the mean of Y squared. And then you sum each one of those and multiply by each other. And then you take the square root. We did say correlations give you information such as if you have negative correlation, which means that they are varying in opposite directions. If you have positive correlations, it means that they are varying in the same directions. For example, if you had something like this, and you have this as your X1, and then you have this as your Y. In this example, it's just X and Y, not X1. So these will have positive correlations in the sense that they are varying the same. But if you instead had something like this, where you had X going this way, it doesn't always have to start from 0, and then maybe Y going this way, then you have a negative correlation. And we also say you might have a 0 correlation where maybe X is varying in a different direction and Y is varying. 0 correlation means you cannot conclude, basically. You can't say whether the two variables are varying in the same way. So the more strong correlations you have, the more closer these two are. And in that case, their measurements are about the same. And if their measurements are about the same, they have the same information. The reason why I said correlations will let you know whether and how to draw conclusions as well. Because if you do correlations and realize that the values are very similar, it means that you could interpret your results in different ways using those correlations.
Okay, if I may ask, please.
Yes.
What is the interpretation we give to a 0 correlation?
Non-conclusive, you cannot conclude.
No, what I'm trying to find out is, imagine you are working with two variables and you want to find out whether there's a relationship between those two variables. And then you discover that you can't conclude there is no, that it has a 0.
It means either there is a non-linear relation. Well, you can speculate a non-linear relationship. Correlations work for a linear relationship. So if they are non-linear, you have a situation where you have X1 something like this and X2 maybe a tangent function. So this is your X1. If your data vary in this way, suppose your variables were X1 and X2, this can be non-linear, which means you can't really say something. You can't use correlation. You have to use different kind of study to study the relationship between these. If it's in the machine learning, then maybe you can use a non-linear model like a neural networks and things like that. But here, for statistical purposes, what the most you can say is probably that you have a non-linear relationship. And if you have a non-linear relationship, it means you can never infer the behavior of one variable from the other, because you need to actually study. If you wanted to dig further, you should plot the relationship individually and see how they are. And then you might get an idea of what to say about it. So it simply means that the relationship, correlations only capture linear relationships. Linear means they are sort of a line, right? Increasing as a line or decreasing as a line. All right, so we talk about correlations and linear and nonlinear relationships. One of the things that is so beautiful that we have not discussed is linear regression. That's because we are getting more into maybe statistics and little outside of statistics. So linear regression, simple linear regression is also a method which can be used to study. That's probably the area I would have been very comfortable discussing with you. Suppose you have two values, y and x. Suppose these are students and these are scores, right? You want to study the relationship between student scores, and then you say these are the ranges of scores, maybe 0, 5, 10, and so on. And then you map the students against their scores, and one student score here, another student score there, another one scores here, another one score there, and so on. These are the points which represent the. So what the simple linear regression model does is that it looks for a linear relationship between the students and their scores, or maybe say it was student 2 scores or whatever. You look at the matching between the scores. And then what it does is that it looks for a line. It puts multiple different lines here, linear. It looks for the line that best fit the scores. If I get a different color, say blue. So it looks for different lines until it finds the best line, which divide the data in such a way that the errors are the minimum. The errors are how far away is this from this line? This is an error. How far away is this from this line? This is an error. How far away is this from this line? This is an error. So it measures these errors, square them, and take the square root. The smaller the error is, the better is the linear relationship, or the better is the linear model. The coefficients here, A and B are called coefficients, are determined by how close this line lies here. So the model basically look for the best coefficient such that the line is as close to these points as possible. So you get a simple linear regression model. Those errors can be computed using something like this. You don't need to worry about that for now. Base knowledge is that a simple linear regression model, which is a model, can be obtained by fitting a line into measurements between two variables. And once you do that and you get the baseline, what you simply have is the coefficients A and B. So for every given student value X, you can predict Y using that line because A and B are already numbers. Suppose you do that and you get a Y equal to 2 plus 5B. That's your model. 5X, sorry. That's your model. So if X is equal to 3, for a student score that you don't know the corresponding Y, you simply put that here and you get the corresponding Y. And that's what you say that the model measures can be used to do a prediction. You call that a prediction. Now, I don't think, again, that there's not much to worry about this for now, but you have an idea of what a simple linear regression model is or what it does. And I think it's enough at that point. And then we can go further and look at some other examples. Unless you have a question. How do I delete everything at once? Not have to delete each thing separately. So in this example, you have the coefficients from these data points, and the coefficients are calculated, so you get a model. So moving further, we would look at some examples. I think Grace would be happy if she sees an exam question. All right. So for multiple regressions, it's the same thing, but you're dealing with not just two variables. You're dealing with more than one variable. So here you have x1, x2, and then you have corresponding coefficients. So we leave that at that. Path analysis is something that also was pointed in the syllabus. So it examines direct and indirect effect amongst variables using either multiple regression or multiple regression equations that we've seen, that I just briefly mentioned here, which is a generalization of simple linear regression. You draw a path diagram and calculate the direct and indirect effects. So for instance, if you were looking at relations between variables x, y, and z, you want to do path analysis to understand how to examine the direct and the indirect effects between x, y, and z. You have a sort of a multilinear regression setup here where you have for y the relationship with x and z with their respective coefficients, and then you have another that describes the relationship between z and x with their respective coefficients. It could have still been just one with all the three. So the direct effect of x on y, the b1, the indirect effect of x, y, and z is through z, which is b2 multiplied by b3. So the effect is really determined by these coefficients. So the indirect effect of x on z through z is determined by the product of b3 and b2, because you see that x and z are related here by b2 here, and x and z are related here by b3 here. So again, this is maybe just very, very narrow or very simple way of thinking about it. I don't think we had enough time to discuss this, because I think we should look at the exams before we round up for today. Let's see what time it is now. We're already way past the time we promised. So the last thing is just look at a question, which I think in the past exams, there's often the tendency, I've been talking about things that may or may not, but there's a tendency that you would have a table and you might have to calculate frequencies and frequency distributions and so on. So given the following frequency distribution, we know what a frequency distribution is, right? A frequency distribution is basically for every category, how many times did that value appear in the data? The score 20 appears 12 times, 18 appears 15 times, 17, 14 times, and so on. You understand the idea. You can be asked to calculate the mean or the mode given a frequency table. And I hope Grace is still here. Is she there or she left? She left, unfortunately.
No, she's there.
She's there but busy. She's not even hearing what we're saying. So you can be asked to calculate the mode. How do you calculate the mode or the mean if you are given a frequency? I don't know if anybody recall this, but we discussed this. We said to calculate the mode, you calculate the mean multiplied by the frequency, and then you sum that. The sum of the frequency values multiplied by the values themselves, and then you sum that and you divide by the sum of the frequencies. I don't know if you remember this formula. So for the mean, our frequency values for 20 is one value whose frequency is 12. So we multiply 20 by 12 plus the next value is 18, whose frequency is 15, and so on and so forth. So that's what this first part does. The second part is the sum of the frequencies. So in some way, it's a weighted mean, and then you get your mean. How do you calculate the mode? I leave that one as an assignment for you to do. So you could also be given a question to calculate the variability. So given the data set here, how do you to calculate the variability or the range or the standard deviation? I would expect many of you who have at least make an effort to be able to get those kind of points very easily. We talked about the range several times. We use it several times. We talk about the variance even today and the standard deviation. So really, there's no reason to spend time on that one, right? So we can just skip that and you can look at it. So you could be given a question on the t-test where you, for instance, this is actually a past question. A researcher claims that the average IQ of students at a university is above 110. This was an exams questions from previous year. So a sample of 36 students has a mean IQ of 113, which is a standard deviation of 12. This is where you need to know, first of all, you know the different conditions. Who is not muted here, so I can mute them. Good. So you know the different conditions, and the most important condition, one of them we've seen is that you know or you don't know the standard deviation of the population. So look at the question again. It says that a researcher claims that the average IQ of students at the university is above 110. This is talking about the average IQ of students at a university. So the population is the university here. The statistic that, or the claim that you need to formulate your hypothesis is the fact that the average IQ has a specific value of 110. Now, we don't have data about the complete population. We have data about a sample of 36 students. So your population is the university, your sample is 36 students, and their average IQ. I don't know that I like this very much, this word. The mean IQ turned out to be 113. Why I said that is because it's difficult to measure this exact. And the standard deviation of that is 12. That is the sample. So the sample gave you this. So test this claim with a significance level of 0.05. This is 8 points that you should be able to get. So first, what is your null hypothesis? What is your alternative hypothesis? Is there any student who can try, who would like to give this a try? Just a quick response to that. You want to try, Odelia? Since you're unmuted. What is the null hypothesis and what is the alternative hypothesis? Nobody wants to try that? Calculate the t-statistic. So are we going to calculate the one sample or the paired sample here? Find the critical value and make a decision. What did we say was a hypothesis, a claim, a statement? In this question, what is the null hypothesis here? I think it should be very obvious or simple. I would not answer the question about the null hypothesis. I want you to try that and get back to me if you can't find the response. Because I think it should be very straightforward. So, but we'll go ahead and answer the other questions. So we know that the sample and the population mean are 110 and 113, and we know the alpha is 0.05. So we know the X bar, we know S, and we know the mu. And therefore, we can simply use that in a t-statistic formula, which we've seen before. And to answer this question, you need to know this formula, which is basically the mean, which you've been given. minus the mean of the population which you've been given, and then you divide that by the standard deviation of the sample and the square root. And the conditions, you have not even been asked to check the conditions. You have just been asked to calculate the t-statistic to make a decision. So the degree of freedom is 35. And then you know that the critical value here, you have the alpha of 0.05. The question then is, I don't know whether they give you this value here, which is what we refer from the graph. In my opinion, I think the question will be hard for you to answer if you don't know what the corresponding significant value for alpha equals to 0.05 is. So the decision to make would depend on the comparison between your critical value and the calculated value that you get from t here. And the calculated value is 1.5. So if you have a value of t that is far greater than your critical value, then it's an evidence against the null hypothesis, and you would have to reject the null hypothesis. In this case, we calculated 1.5, and 1.5 is less than 1.6, which is the corresponding value of the p significant equal to 0.05, which fails to reject the null hypothesis, and therefore the alternative hypothesis has to be true. Or at least insufficient to evidence to conclude that the mean IQ is above 110. So in some sense, you admit the alternative by rejecting the null. You can't reject the null. The assumptions which I've asked, I will just keep that. You can review that by yourself. The assumptions for the PET test I ask, I will skip that. The assumptions for the ANOVA, I will skip that. Those are things you should review. We also talk about the Z-test and also the conditions for doing that. I will not repeat and read that to you, but I will look at a different question. So the following scores, this is again a question from the exams. The following scores are obtained by a physics teacher after administering a test to 100 students in a class. Again, the same frequency, but this time we have the intervals, not the specific, how many times the specific value appear, but more like between 0 and 2, we got 8 values. Between 3 and 5, we got 8 values. Between 6 and 8, we got 12 values, and so on. So you get a frequency table like this as the scores obtained by physics teacher for a test of 100. 8 students scored were between 0 and 2. 5 students scored between 27 and 29. So to analyze this test scores, we could still do the same calculation. We can be asked questions such as, what is the class size? To calculate the class size from a frequency table, you take the difference between the upper and lower bound and you add 1, which is something we also have mentioned. The lower bound here is 0 because the lower bound is this n of this, and the upper bound is the difference between the upper bound and the lower bound, and you add 1 to it, which is for the using the first class 0 to 2, you can calculate the difference between the lower and the upper bound, and you add 1 to it, and you get 3. And you do that for the other classes as well. So once you get the difference between the upper and the lower bound, your lower true limit, because this question asks you to calculate the lower true limits. Your lower true limit would be the lower bound minus 0.5, which you can obtain that by calculating the first interval, which is 0 to 0 minus 0.5, which gives you minus 0.5. The upper true limit would be the upper bound plus 0.5, which is the last interval here, which is 29, plus 0.5, which gives you 29.5. If you did not understand that, you can look at this calculation here. The midpoints, you can then go further to calculate the midpoints for each of the classes. For the first class, 0 plus 2 divided by 2, 3 plus 5 divided by 2, and so on. So you get again the lower bound plus the upper bound divided by 2. So the lower bound, again, the same lower bound that we're talking about here. If you don't understand that, you'll get that more from here, what the lower bounds are for each of the intervals or classes. So once you get those, you can again do the relative frequency calculations. These are the scores on 100, so the total was 100. And so the relative frequencies will be the corresponding frequencies here, which is the percentages. And you can use that then to calculate your mean. Multiplying this and then summing them up and dividing by the sum of the frequencies, which is another example that we've seen. Then there was something on histograms here. We talked about histograms and bar chart and things like that, because you might also be asked to describe what information you can get from there and the differences between these two. Now, I was in a bit of a hurry here because I know you have another lecture and some students have started leaving. Is there any question? The point with this material is that you can use this to practice for your exams. So you have an idea. What I was looking at were questions that have a lot of points. You have multiple questions with just concepts, which if you read, you should be able to pass. Describing concept, defining concepts, or multiple choice or something. But these are the questions which are a little bit involved, which you might be able, for those who read and understand, get 10 points, and that would contribute a long way to you getting a good grade. Is there any question before we round up here and you go for the rest of your day? We are almost half hour more than planned. I also know it's a Saturday, but I know you have something else that is coming up today.